Hey guys, in this video we will be looking at the conjugate gradient method. It is a method for finding the solution to linear systems under the minimum number of steps. So for an n into n matrix, in this case it is the matrix A, we can find the solution to this equation under n steps. So that is a great improvement in comparison to other methods like the Jacobi method and the Gauss-Seidel method. So first we will see how this method works and then we will go to implement this in C++23. Here is the basic idea for the conjugate gradient method. So it's a combination of line search and Gram-Schmidt method. So we have the x0 and x. x0 is the guess and x the actual solution. And we have to take a certain path to achieve the solution in the minimum number of steps. So you will see here we have two paths, the one that is red and the other one is green. So you will come to understand that this algorithm in two steps. The first step is to actually compute the x value and then we will update the actual direction of p, that's the path. So it's a two process algorithm. And if you do not do the second step, this algorithm will overshoot the result and we will get a result that is so far away from the actual solution. So that is shown by the green arrow. So this is the algorithm for the conjugate gradient method. It is a 4-step process. Actually it is just 2. I have enlarged it for better understanding. So the first step is to set this r vector to b minus ax. B is the constants that we know, a is the matrix and x is the initial guess, x0 actually. Then we set p. P is like the direction. Now r is like the value that is tied to the actual matrix. P is the direction, x is the initial guess, alpha and beta are just scalar values. Alright, now based on this r, we find alpha. Alpha is the value that we will use to update the x value. You know that x is the actual value that we have to find and alpha is just the coefficient that we multiply with the direction, so we get a new point. Alpha is r transpose times r whole divided by p transpose times a times p. So it seems like a bit of jargon but it's actually very simple stuff. You can refer the documents I have linked. The derivation part of this algorithm is out of the scope of this video, so I will just go over this, and from this x value we find new r values. See, it's basically the same equation that we use here, but we replace this x value with the new x value that we find. So it boils down to this, just r previous minus alpha times a times p, and then we have to update this p vector. So this is like the direction, right? We update that using this beta scalar. Now we find beta by this equation where it is given by r transpose times r. So this is the new r values, and then we divide that with the old r values, exactly the same equation. So it's like a coefficient that we will multiply with the previous p value and sum that with the new r value, and we will get a new direction. So this is the algorithm. It's a little bit hard to understand it in the first try. I will link the relevant documents and you can see the derivation of that. Now the question comes, where to stop this algorithm? We have two options. The first one and the most beautiful part about this algorithm is that it takes very less number of steps. So for example, if the order of the matrix is for example 30 times 30, let's say there is like 30 rows and 30 columns, this algorithm will find the solution in less than 30 steps. So that's a lot of improvement comparing to other methods. And the other way is to set tolerance value. So maybe we do not want to go up to 30, maybe we will find the record value for example at 10 or something. So we can compare this r value, we take the norm of that and we check if the magnitude is less than the tolerance. So if that matches the condition, we exit out of the loop and we find the value. Now let us implement this in C++. So this is a function which takes in 4 parameters. The first one, A, is the input matrix. B and X are vectors but represented as 2-dimensional matrix for easy computation. So B is the constants and X is the initial guess. And we also provide a tolerance value which we will use later down the code. The first step is to find the value of R0, which is going to be the initial value of R. The formula is B minus A x0. x0 is the initial guess. And we know that we set the value of p to r0 initially. Now we get into the loop. The loop goes from 0 to the size of the b vector. So the very first step, which is not included in the actual algorithm, is to check for the tolerance. So the key for the tolerance is the value of r. So we convert this 2-dimensional r into a 1-dimensional vector using transforms, and we check if the norm or the magnitude is less than the tolerance value. Then step 1 is to find the value of r transpose times r. But r is a 1-dimensional vector, so we can just multiply the elements with itself and add all those elements together to get the value of RTR, which stands for R transpose times R. The next step is to find the value of P transpose times A times P. Since A and P are non-values, we can just multiply them together using this utility function. Then we multiply this result AP with the value of P transpose. Instead of creating a new matrix for P transpose, we will just multiply these two together using a simple for loop, because the result AP is just a 1-dimensional vector. Now we get into finding the scalar value alpha. So from the slide we know that the value of alpha is R transpose R by P transpose AP. So we find the value and we set alpha. Now step 4 is to find the new x. So remember that x is the actual value that we are finding. Everything else comes down to this statement. Now the new value of x is just adding the previous value with the scalar multiple of p vector and alpha. P is like the direction. Now we need to find the new r vector. So r new is just adding r with the scalar multiple of ap and negative alpha. Now comes the part where we find the value of beta, because we need to change the actual search direction of p vector. So we find the r new vector transpose times r new vector is the same thing we did over here, and then we find the value of beta. Because we already know this value rtr, we divide this new rn trn by this rtr, we find the new beta. Now we add the value of r new and the scalar multiple of p and beta to find the new value of p. Now we got a new search direction. Only after this we set the new value of x and r. Now there is two ways this loop can stop. The first one is that the loop reaches the end condition. The other one is that it reaches the tolerance value. Either of these conditions will reach first and we will exit out of the loop. Now let us run this program. Now here is the test case. A is the input matrix and B is the constants. Now we need to find the x vector that comes between this. So first we print both of these matrices. Actually this is a vector. Now we create the initial guess. It is all zeros by default. We can change that if we want to, and we plug all these values inside this function and we print the result. So I have a script for running this program. Let's run that. As you can see, we get 4 values. These are the accurate values of x. The actual values are 1, 2, minus 1, 1, and these values are very close to the correct result. So yeah, this is the conjugate gradient method in C++ 23, and I will see you in the next one.